Okay, so section 4.3, we're going to talk about fitting lines to data, or curve fitting, linear curve fitting approach. So I'm going to start out here by talking about this data set, which is pretty linear. So this column, first column are X, the on-base percentage are my X values, and my Y values are my runs. And this information pertains to 2017 National League Baseball runs scored versus on-base percentages. So for the different teams like the Arizona Diamondbacks, I think, and the Atlanta Braves, Chicago Cubs, I think, Cincinnati Reds, Colorado Rockies, LA Dodgers maybe. But okay, it's not a lesson in baseball, but just to know, on base percentage is this. These are seasonal values, I think, and so this is an average. 30, for example, for Arizona is 32.9%. That's how often when a person steps up to bat, they get a hit and get at least to first base. So that's the percentage for all the players over the season, and then you have the number of runs the team scored over the season. So we're comparing getting on base. How does it compare to runs scored? And we want to see if this is like a linear relationship. Okay, well, instead of doing a bunch of work by hand, what you can do is you can take this information and we can copy it to a program like Microsoft Excel. Now here I've opened up Excel. Now you have free access to this, and this is the version of Excel that's available through the, unfortunately you can't see the menus because I have them above what I'm showing here, but I have reproduced this information. Well, actually I just copied this information back to the other page, but this is where you can reproduce this information, and the key here is you want to have your X values. A good way to set this up is you put your X values first, and then followed by your, in the very next column, by your Y values. And the reason you do this is because it makes setting up a plot of this information really easy, and that's what we're going to do next. We're going to set up a scatter plot. So in order to do that, so I call that I got to open up the pens here. So what we're going to do is we're going to set up a scatter plot, which is essentially a plot, Cartesian plot, with the x-axis and the y-axis, and this information as point pairs set up in it. So the way to do that is, you can't see the menu up at the top, but oh crap, I accidentally saved this. I didn't want to. If I could go back and unsave it. Nope. Is you press the insert button, and then you look over to the right in the section in the menu that says charts, and you select, in the chart section you select scatter plot. But before I do that, I want to highlight these two columns. So you want to create a box around these two columns. So you left click on the first number, then hold the left mouse button down and drag, and if you move over to the right, you get into the other column. You want to make sure you drag so you have all the numbers highlighted exactly like I do. And now you want to press the insert, and let's do a scatter plot. So now this automatically then, by default, this way you don't have to set anything up. By default, this sets up a chart where the x-axis is associated with your left column and the y-axis is associated with your right column. And then it plots the individual points, and you can see the point pair. Here's 30.9 and 639. So that's associated with San Francisco down here. 30.9, 639. So what's nice now is that I've got this set up in a nice little plot, and we can modify this. I can click on the chart here, and I can put in information. I think what I want to put in is the same information I have here. So I'm just going to copy it, runs scored, and this will change my chart a lot, the aspect of my chart a lot. Let's just use this paste button. Paste. Okay. So I pasted that in there. So if you're going to make a chart that is a solid chart that you want to have in maybe a document or something, showing something I want to show later, you always want to have an aspect ratio where your chart is taller than it is wide. If you go look in any reputable periodical or journal that you post to, charts appear like this. They're higher aspect ratio than they are wide. Okay, so I like the way that it by default set up the x-axis between 29 and 34. That's fine. Now notice it starts at 29. 0 is way over here. So I could take this information and I can change my axis. I like this, but what I'm going to do is I'm going to change it just to show you. So I right click on the axis information and I say format axis. And here in axis options there's a number of different headings you can have, but make sure you're on axis options, and it starts at 29. I could have it start at 0, and if I hit enter it'll do that. But look at what it does to my chart. It puts all my information up here in the so now when both the y-axis and the x-axis start at 0 and my origin is in the correct spot, it puts my chart way over here. Now that's kind of interesting because we can see if I draw a straight line through this that my intercept is going to be a negative value. That's kind of cool. That doesn't make a lot of sense, but that's how a line would work there. But this doesn't look very good as a way to present information. So what I'm going to do is change this back to what it was before, and I think it was 29. Let's just make it, well, 30 is too big because that includes that dot. So let's make it 25, and 25 is too small. I guess 29 was good. So the program did me right there. So 29 to 35 is what I'm representing. So I'm only representing the corner up there. But this goes from 0 to 900, and I don't like that. It's showing too much dead space down here. So I'm going to do the same thing over here, and I'm going to choose a number. We could go 500. 500 looks good. And you know, it's just what's pleasing. Okay, so now I have a plot that represents information. Oops. And while I was doing that, I think I can get rid of my grid lines too. I'll do that later. Okay, so now I have this plot. I guess I'll bring it back over here. You can move these things around. Bring it over here because there's buttons here we want to use. And the last thing I need to do is, you can't just slap a plot like this and turn it in if you're doing a project or something. You got to label your axes so that people understand what things are. So I need axis titles. I have a chart title, I have axes. I can turn my grid lines off now, which I'm going to do because they also don't look very nice. 6-1. I don't really need data labels, and I don't need a legend since there's only one data set here. So this looks good. Now I've just got to edit these axis titles. So I'll call this runs. No, on base. This is on base. On base percentage. So same thing I have written over there. Could copy and paste it, but and you can automatically set this up too, but it's a little more troublesome. Runs. Okay, so now this thing looks like a decent plot. So this actually is portraying information. And as I look at this information now, I see that it is linear in nature. I could very easily take a line and draw a straight line, and it's going to be tough for me to draw a straight line here, but I'm going to try. I could draw a straight line through this and say, oh, this models the data. But the problem is, you could come and you could draw this line, and you could say, oh, this line, this linear line models the data. You could take 2 points, and you could draw a line between 2 points. Let's go with blue. And say maybe this line, I could take these 2 points and I could create a line, and I can come up with the slope, of the line, and y equals mx plus b. I could figure out what that is for these lines. But the point here is that each of us would have a different line that we draw through there. So that may be fine and dandy, but who's to say whose is better than anyone else's? So let me get rid of these lines. So what we could do is we could do something called curve fitting, where we use a mathematical approach to this. And the mathematical approach that we use is that the computer does the same thing. The computer will draw a line, and then what the computer does is it looks at every individual point and the vertical distance from this line, and then does the same for this vertical distance, d2. And then it takes and it squares these distances because it wants to add them all together. And if they didn't square them, it would all often end up being 0, or really close to 0, not portraying any information. So it wants to. So we square these. So we'll take the distance and we'll square it, and we'll take this distance and we'll square it. And then we'll add up all those squared distance. We'll sum the squared distances, sum of squares, and we'll see what that number is. And then the computer then will generate another line and do the same thing again. And what it does is it chooses the line that has the least sum of squares. So you often call this the least sum of squares regression approach. Now, in order to get the computer to do that, and that's what this whole lecture is about actually, is what we'll do is we'll left click on the data, like I just did. So it selects all the data in this table, and then I right click and a menu opens up and I add a trend line. Now I'm going to add a trend line here, and I'm going to select linear if it isn't selected already. And I can also come down here and I can have it display the equation and display the r squared value, and I'll show you why that's interesting to us. So now every one of us who does this is going to get the same result for the line. So this is the best fit line based on our least square, sum of least squares approach. And in addition to that, so here's the equation for my line: 57.5x minus 1125.6. So remember I said it looked like it did cross the y-axis in the negative. But this is a model for this data. And the r squared, what it does is, if I take the square root of that, and that's why I have this number over here so I can remember what it is, so I quickly bring it over there. I'll just write it again. R equals 0.94. Again, that's the square root of this r squared. The closer this is to 1, the closer this fits a linear function. So 0.94 is pretty close to 1. So this is a pretty good correlation between on-base percentage. So it means there's a pretty good correlation between on-base percentage and runs that a team scored. So if you know what a team's on-base percentage is, you could probably predict how many runs the team's going to score over the course of the year. So that's how you use a model like this. So I can make a prediction based on whatever I want now. That I have this y equals 57.5 minus 1125.6 equation for a line. So in summary, Excel is a really useful tool for scientists to use to help them manage data. And I think if you start to use it a little bit, you'll find that you can get some use out of it for some of your other classes.